This is a presentation on generative biomedical entity linking by Saptarshi Basu and Russell Taylor. We'll cover an introduction, scope of reproducibility, our data, models, results, future work, and references. Entity linking is a foundational problem in healthcare. Medical records are kept in different formats and different terminologies, and recent papers have leveraged deep learning models to map mentions of medical concepts to standard terminologies. But this paper improves upon those approaches using generative language modeling rather than classification. Like earlier approaches, this paper proposes two-stage fine-tuning of a large language model. The first stage injects the model with synonyms and definitions knowledge from UMLS. The second stage trains the model on annotated mentions in biomedical texts. The generative approach requires creating synthetic natural language datasets, but it allows fine-tuning to be done with a smaller memory footprint. The original paper achieved state-of-the-art results on the biomedical entity linking task, and our results confirm both the usefulness of this approach and the prohibitively expensive compute required for the pre-training step. Our experiments included the impact of fine-tuning, so running the model with only the pre-trained model versus pre-training plus fine-tuning, the impact of the decoder prompt, so the performance with prompting the decoder and without prompting the decoder, and the impact of sampling versus no sampling for the beam search. Our data for the input, for the pre-training step was UMLS, specifically related to semantic types, definitions, and synonyms. For fine-tuning, our data was BC5CDR, which is a database of medical texts that have been annotated for mentions of medical concepts. Here are the total records for the input data for the pre-training, and here are the number of unique CUIs in that data. When we pre-processed the data, we got 213 million distinct sequences, including encoder inputs, decoder inputs, attention masks, and labels. That amounted to 186 gigabytes of total storage, and some challenges in compute and training. We noticed some class imbalance in both the pre-training data and the fine-tuning data. The generative models generally handle class imbalance better than classification models, and we noticed that our model handled it pretty well. We process the data by limiting it to 21 semantic types and to the standard medical ontologies, performing some data cleaning, and then inserting the synonyms and the definitions from UMLS into standard templates in order to create synthetic natural language sequences. For the fine-tuning data, we used the non-synthetic data sets that were annotated with medical mentions, and the targets were the target CUIs that correspond to those mentions. So for pre-training, this is an example of the templates that we used. So the concept from UMLS is defined as the corresponding definition from UMLS. Our model architecture was BART for conditional generation, which is a bidirectional encoder plus autoregressive decoder. You can see the architecture on the left, 12 layers of standard transformer architecture, and then a text prediction head at the end for generative output. We implemented parameter-efficient fine-tuning in the pre-training step, specifically LoRa, to reduce the number of trainable parameters and improve compute time with minimal information loss. The objective of our training was to output the most appropriate CUI for a given mention in a medical text. So for example, you have a CUI here on the left, and with the synonyms and definitions, we inputted those to the clause templates in the pre-training step. You can see a couple examples of that. For fine-tuning, we have the med mentions data, and the output is the standard terminology. For pre-training, the input to the encoder is our synthetic data built from the templates, and the input to the decoder is the concept name plus the word is, and the output is the corresponding synonym. For the fine-tuning step, the input to the decoder and the output to the decoder are basically the same, except for the mention was chosen using TF-IDF to choose the best one. And the input to the encoder is the med mentions data with its context. So at this point, I will turn it over to Rishi.
Thanks, Russell, for the overview. We now look at the generation workflow. We have the BART architecture that undergoes UMLS-based pre-training and synonym-aware fine-tuning. During generation, we use the encoder hidden state and the optional decoder prompt, followed by prefix-constraint beam search to generate an output. That output is mapped to a dictionary that maps synonyms to concept using the UMLS mesh ontology, and the output concept is then compared with the ground truth for precision calculations. We now focus our attention to the prefix tree constraint beam search, as it is key to ensure that the model does not hallucinate. At the back end is the trie data structure that ensures that each token is followed by only acceptable tokens that ensure that the resultant word is part of the UMLS knowledge base. This prefix tree constraint is applied during the generation process using beam search so that each generated token has to meet the constraint created by this prefix tree, and that ensures that the output is always part of the UMLS knowledge base. If we now use that generated output and compare it with the ground truth level, we'll get the precision metric, and that is used to test the different hypotheses. First, we show that the fine-tuned and pre-trained model is superior to the fine-tuned, the pre-trained only model for all cases. Then we show that the no sample case is superior to the with sample case as it is more consistent and repetitive. Then we demonstrate that the with decoder prompt case is superior for both pre-trained only and fine-tuned model for the with sample case. For the no sample case, we can show that the pre-trained model with prompt is superior to the no prompt case. But for the fine-tuned model, the no prompt actually performs better than the with prompt in our study because of computational limitations. We could complete the training for no prompt with the optimal hyperparameters, which we couldn't do with the with prompt due to GPU constraints. When we compare results with the reference paper, we can see for the without prompt case, the results are pretty similar for both pre-training and fine-tuning. For the with prompt case, with only pre-training, our model performs superior. However, this is because we tested our model on a limited dataset compared to the reference paper. On the fine-tuning case, due to GPU limitations, we couldn't complete the hyperparameter tuning for the with prompt case, and hence our results were poorer compared to the reference paper. We can see clearly that the fine-tuned model performs better than the pre-trained only BART model, both in terms of more varied responses as well as the fact that it's more accurate. That is also evident in the concept calls, as you can see in the green versus the red, that the repetitions are less and the more accurate calls with the fine-tuned model compared to the pre-trained only model. If we next look at the discussion and the future work, we could reproduce the results in spite of limitations in computing resources and the complexity of the problem. In terms of hypothesis testing, we showed that fine-tuning improves precision, and no sample beam search is superior to with sample beam search, and decoder prompt improves performance. However, it requires additional hyperparameter tuning to get the best results. There are some issues with the paper, challenges like redundant customization, lack of consistency between the code and the text, and we could circumvent some of this problem by reproducing the paper using simplified workflow using Hugging Face libraries, as well as introducing PFT training for parameter space reduction and some novel beam search strategies. For future work, we'll be looking to complete the fine-tuning process with the right hyperparameters and explore additional datasets and new models like L5 and GPT architecture. We have also provided the references and appendix. Please refer to this presentation as well as our draft report for additional details. Thank you.